Boolean circuits and garbled circuits.
Well, thank you very much for the nice introduction. I'm very excited to be here and talk to you guys today, and I'd like to express my appreciation to the organizers. So in preparing for this talk, basically, I tried to put myself in the shoes of somebody who kind of knows what a garbled circuit is and has, maybe seen the textbook way that you get garbled circuits, and you kind of know how it works. You can garble Boolean circuits. But then maybe you've noticed that the past 10 years, and especially maybe the past 5 years, there's been many, many works showing actually you can do slightly more inside a garbled program than expressive Boolean circuit. And when I mean do more, what I mean in today's talk is I'm worried about efficiency. So sort of the applied side, trying to drive down the concrete cost, the asymptotic and the concrete cost of doing specific tasks inside a garbled circuit. And so my goal today is not to explain to you how every single result over the past 10 years works, but rather to give you a slightly enriched mental model for what you can do inside of a garbled circuit that kind of helps to explain why you can do more than just garble Boolean circuits. Okay, so that's really the goal. So again, I think we know this. We're talking about secure two-party computation. Alice and Bob have some program P they'd like to compute on their joined inputs. And they'd like to do this securely. And today we're going to instantiate this functionality with a garbled circuit. So the idea, again, is we have some program we'd like to compute, and the solution based off garbled circuits is basically we're going to take this program P, and we're going to spit out some kind of randomized encoding of this program P. Okay? And basically what happens is one of our parties, let's say the garbler, is going to generate this encoding and send it to the second party, the so-called evaluator. And in addition, the garbler is going to convey to the evaluator some kind of encoding of the party inputs. Okay? And this conveying of inputs has to do with Oblivious transfer if you want to do 2PC, but today we're just worried about the encoding itself. Okay? And then once the evaluator has these encodings, basically everything at this point is local. The evaluator takes this encoding of the program, they take these encodings of the inputs, they can evaluate locally and get the output of the computation. Okay? And really it's the encoding itself that we're worried about today, this thing, the garbled circuit. Yeah, and just very quickly, the security definition that you really care about is privacy, which just says, okay, the stuff that the evaluator sees can be simulated by the output of the program and the program itself. Okay? Okay, so garbled circuits are great because they help us build really interesting MPC protocols, in particular protocols that achieve constant round complexity. Okay, so this is probably the main reason we care. And another reason is that most of the techniques that we know rely only on fast, and in particular the techniques I'm going to talk about today, rely only on fast symmetric key primitives. Okay, so you just need a hash function. Okay, so today we're just going to work in the random oracle model, keep things simple. Just give me a hash function. What kind of encodings can I produce? That's really the question I want to answer today. But the problem with this technique is that this encoding of the program turns out to be very large. Normally, we're expecting to pay some sort of blow up on the order of the security parameter or more, depending on what the program is. Okay? And so really, the task we're going to worry about today is just, okay, let's say we have some kind of encoding of some computational task. What I'd like to do is find a way to do the same computational task, but with a much smaller encoding, hopefully asymptotically smaller. Okay? Any questions up to this point? Hopefully this is all straightforward. Okay. Oh, I wrote 2 routes. I changed my slides last minute. There's sort of 3 routes to do this garbling of programs. I added this first one because Yuval was talking about it. So there are three kind of approaches. We're going to focus on the second one. Basically, we're going to be in the symmetric key setting, okay, where we have a hash function. And again, for today, we're going to just say it's a random oracle. It turns out you can establish some kind of concrete property of the random oracle for all the things we're going to talk about, but I don't want to get into that level of detail today. Okay, and then later today, we're going to hear about some very exciting work that takes a stronger assumption than just, okay, I have a hash function that takes some sort of structured assumption like ring LWE or something like this, and you can get more. Okay, but today we're focusing just on hash functions. Okay, so I went back and I watched Mike Rosalek's talk at Simon's 10 years ago, and he gave an excellent talk where he sort of described the history of garbled circuit research up to 2015. And that story was sort of beautiful and very straightforward and nice, because up to that point, we knew very little, except for that basically you can take a Boolean circuit and you can construct an encoding of roughly 2 times the circuit size times the security parameter, okay? And outside of this, we didn't know too much. There were some beginnings of things. I think Garbled RAM had come onto the scene some 1.5 years earlier, something like this. But this is more or less where things stood. But the problem with Boolean circuits is that there are many computational tasks which do not efficiently compile down to a Boolean circuit. Okay? So in the last few years, you may have seen some papers that do things like this, that do arithmetic circuits, that do RAM programs, that do programs with conditional branching, do lookup tables, do fancy bit vector operations, all sorts of different things that's sort of trimming down the cost of compiling into a garbled program, into this encoding, and getting a smaller encoding out of all these different problems. And now, of course, there are other dimensions of garbled circuits you might be interested in other than what I'm talking about today. But basically, this problem of circuit garbling is currently very, very active. And some evidence of this is that at this year's Crypto, there are 3 entire sessions on this topic, which I think is amazing. OK. So yeah, here is just some papers. A lot of these are mine, not all of them, but showing different kinds of things you can do with garbled circuits. And again, I'm envisioning that many of you say, OK, well, fine, that's complicated. I'm sure there's some way to do it. Cool, and move on with your life. And what I hope to do today is try to give you a sense, again, some kind of core ideas to give you an improved mental model of what a garbled circuit is capable of that sort of helps to explain part or all of some of these different advances, okay? So suppose you come to me and you say, David, I have some particular computational task. I would like to encode that computational task such that we can carry it out in a garbled circuit-based constant round protocol. What are my options, okay? So it used to be that the options were basically, take your program and express it as a Boolean circuit, or go off and build your own protocol and do the whole work of writing a paper and proving it's secure, and then you're good, right? And the problem with these is that, again, this is not always the most efficient. Boolean circuit encodings are not always the best. You can suffer polynomial blowup. And me just telling you go build your own protocol is not very helpful. Okay, so what I would like to do today is give you, take Boolean circuits as your first order approximation of what a garbled circuit can do. And what I'd like to give you today is a kind of second order approximation of what a garbled circuit can do. And that is going to be called something called a switch system. I call a switch system. So this is a model of computation that, cards on the table, I made this up. But this is my mental model for understanding what a garbled circuit is capable of. And the point is that if you have a computation and you think carefully, you can often take that computation and turn it into a much smaller switch system than you can a corresponding Boolean circuit for the same task. Okay? That's the point. This is just the papers that this observation is based on, how I was sort of arriving at this idea. And just to make sure we're hammering this home, you start with some computational task that you have P. Option 1, compile it to a Boolean circuit. Option 2, compile it to this other model of computation, which is called a switch system, which I'm going to describe to you. It's a circuit-like thing. Okay? It's not too scary. It is more involved than a Boolean circuit. Okay? That's why I'm saying take it as a second order of approximation of what it's capable of, rather than the highest level. But otherwise, the procedure is the same. Take your computation, compile it down to some kind of circuit model. And then when you garble that thing, the hope is that at the end of the day, you get a smaller encoding than if you had gone on the top route. OK? All right. So switch systems can, again, partially, meaning there is some kind of hint of these ideas in the papers, or in some cases completely describe what we know about some of these advances. Okay? And so in particular today, I'm going to focus on this problem of garbling arithmetic programs, arithmetic circuits, starting from just a hash function. And if we have time, though, I'm kind of doubting we will, I'll also explain briefly how you sketch how you get RAM programs out of this model. Okay. So that's the plan. So before I describe this model to you, tell you its rules, and then start illustrating how you can use it, I'd like to show you, tell you kind of what you can expect to get out of this. So the most dramatic result that we know is that, so if you have a word RAM program, so you have some kind of program that is every CPU cycle is reading something from a RAM, and let's say it runs for t steps, and let's say that the things stored in the memory are words of size log t for simplicity. Then if you take this word RAM program and compile it to a Boolean circuit, you're going to get something that scales roughly quadratically with the runtime of the program. And the reason for that is basically every single time your word RAM program does anything, you have to go through and read every single slot of memory in order to figure out if that's the thing you're looking for or not. Okay? So in contrast, if you have one of these switch systems, you can get a switch system which is t times some polylog factor, which is on the board. Okay, so the overhead is tremendously better. Right? But yeah, the one that I want to talk to you today about is arithmetic circuits. So consider you have an arithmetic circuit over m-bit integers. Maybe it's in some modulus. Choose any modulus you like. Okay, if you take that program and you compile it to a Boolean circuit, you'll get something. If you use some kind of school book algorithm for multiplying numbers, you'll get an encoding which scales with m squared, if m is the size of bit length of your numbers. Or if you use fancier algorithms, the best known multiplication algorithm is like m log m. Okay? But if you use a switch system, interestingly, you can get a garbled program, a garbled encoding of the arithmetic circuit, which has size only n times m. Okay? So you can do something better than the best known Boolean circuit algorithm for multiplication. Yeah?
Like small values of m are fine.
I'm sorry?
Does m go to infinity?
Yes.
Okay.
Yes. Yeah, I probably should. The size of each gate is at most m squared here, at most m log m here, and at most m here.
I think the question was whether does it only work for large m, or does it also an improvement for small m?
It should be an improvement for all m. Yeah. Okay, so now I want to tell you about this switch system. Oh, yeah.
So how does it compare to the public key-based algorithms?
So the very recent arithmetic ones. So for example, this will be asymptotically worse. Concretely better for small m, and in the asymptote, of course, this loses out. Huh?
It's worth adding it to the code.
Oh, I have it later on.
Ah, okay.
Yeah. Sorry. Okay, right, so I want to tell you how the switch system model works and also how you garble it. So in order to do that, I want to do just a little bit of preliminary work on sort of how modern applied garbled circuits work. And so the starting question is, we have this circuit, and there are wires in the circuit, and the question is going to be, what is the encoding of each wire in the circuit? Okay, so the way that these symmetric key garbled circuit schemes work is that every wire is encoded modularly, it has its own encoding, and so the question is just what is that encoding? Okay, so we're going to use today what's called free XOR labels. All this means is that we have some big circuit, okay, and at the beginning, the garbler is going to sample some correlation, let's call it delta. Okay, so delta is just some lambda bit long string. It's going to be global to the entire computation. And I'm just going to add a little bit of a constraint here, which is the very last bit of this thing. The least significant bit of this thing is going to be a 1. Okay? And then for every wire, each wire in the circuit, each wire is going to have its own, what I'm going to call language. It's going to have its own language, which is itself a lambda bit string. And it's important that all of this wires in your circuit have different languages for security. Okay? Now what happens, remember, the garbler is going to go through and sort of produce this encoding of the circuit, and then later the evaluator is going to run that thing. And the question is, what does the evaluator get on each of the wires? And our answer is going to be that the evaluator is going to get some kind of combination of the language for the wire and delta. Okay, so in particular, if this wire x holds value x, just overload that notation, then she'll get Lx plus the quantity x times delta. Okay, so she either gets Lx if x is 0, or she gets Lx plus delta. Yeah.
X is a number, X is a
Right now, x is a Boolean. It's a bit. Yeah, we'll generalize from that in a moment. Well, later. Any other questions?
And LX, when you write LX, so here X is just the name of the wire.
It's just the name of the wire, yeah.
Okay, so just two values.
Yeah. Just two values, yes. This is the name, x is the name of the wire, Lx is the language for that wire, and then I'm just overloading x is also the value on that wire. Okay, good. Yeah, so just some points to emphasize. This Lx is called the language. This part here that the evaluator called is traditionally called the label that the evaluator computes. And again, we're going to make sure that this delta has a least significant bit of 1. Okay? Another way to view what's going on here, if we just take the garbler's part of this encoding and the evaluator's part of this encoding and look at them together, then pretty clearly what's going on is this is some sort of XOR secret share of the value that's actually on the wire. Okay, so every single wire in the circuit will have a secret share of the form that wire's value multiplied into this correlation. So it's kind of, this delta is sort of acting like a message authentication code, if you like. It's authenticating to the garbled circuit what bit is actually on this wire. Okay? And one point I'd like to make here, so what all this is saying is you got this label, both parties have their parts. Suppose each party takes the least significant bit of their part, you get out a secret share of x. Okay? This trick is historically called point and permutes. Okay? It's not too shocking. It's just saying, basically, because we enforce that delta is a 1, then the least significant bit of these two values forms an XOR secret share. If you think about it for a second, it's pretty clear. And the point here is that it's very easy, in the context of a garbled circuit, to get a hold of a secret share of the value that's on that wire. Okay? All right. I think we're going to need this also for a talk later this afternoon. So any questions about this? I have been forewarned. Okay. One other thing I just want to say, and then we're done with preliminaries, is just that there's a special case thing here that's very, very cheap in a garbled circuit, which is suppose you have some wire which you would like to correspond to part of the garbler's input. Okay, so there's a wire supposed to have a bit on it, but that bit comes from the garbler's input. This part is free because all the parties do is the garbler says, oh yes, my share is x times delta, and the evaluator says, oh yes, I have no idea what x is, but my share is 0. That is an additive share of x times delta. That's a good label for this wire.
So you're not thinking now about garbled circuit as an abstract thing, you're thinking about the concrete scenario of two-party computation.
Yes.
So,
Okay. Yes, the concrete scenario of two-party computation. That's right. Okay. This is going to be important for us later because later on we're going to have the garbler provide lots and lots of input to the program. Okay. In particular, the garbler is going to provide lots of randomness as input to the program, and so it's important for us that this is cheap. Okay. In particular, it's free in the sense that the garbled circuit didn't grow at all from this. The evaluator just, oh yes, my share is 0 for this wire. There was no communication required to arrange this. Okay. All right. All right, so with that background, I can now tell you about what a switch system is. So first of all, a switch system is effectively a circuit model of computation. There are wires, there are gates, okay? And each of those gates performs some kind of primitive action on the wires and computes some small part of the overall computation. But the thing that is distinct about switch systems as compared to, say, a traditional Boolean circuit is that in a traditional Boolean circuit, you have input wires, and the gate does something and puts something on the output wire. Okay? But in a switch system, what's instead going to happen is it's going to be more like each gate is enforcing some kind of constraint. Okay? It's saying something like, these two wires, we'll see concretely what all the gates are. I'm just talking abstractly. It'll say something like, these two wires are in fact equal to each other. And what will happen is the garbler will set up this system of constraints, and then the evaluator will solve it. And the point is that because it's a system of constraints, the evaluator might solve the gates in different orders depending on what the input to the program is. Okay, so we'll see a concrete example of that. This basically gives you a notion of multi-directional gates, and perhaps more importantly, some kind of out-of-order execution. At the time the garbler writes down the program, he doesn't know which order those gates are going to be evaluated in. It's only when the evaluator comes along, she is going to evaluate the gates in some particular order depending on what the input is. Okay? By the way, that might sound problematic from a perspective of privacy, but we'll come back to that in a bit. Okay. All right. So again, we have a circuit model. There's just 3 gates. Okay, so it's not so bad. So let me tell you what these gates are. So we have switches, we have XORs and joins. So let's start with the titular gate, which is called a switch. So a switch takes in 3 wires. It relates 3 wires. One of the wires is going to be distinguished. It's going to be called the control wire. And control wires are going to be very special for us in this model of computation. Okay? And the other wires are called data wires. Okay? And all this gate says is, OK, if this control wire has a 1 on it, then nothing happens. Okay? Nothing happens at all. But if this control wire has a 0 on it, then the switch closes, and now it is the case that y is equal to z. Okay? It's just a model. Yeah.
Everything is bits still?
Yeah, everything is still bits. Yeah, I'll try to be I'll say when we're moving to arithmetic. Yes.
So it's just relations, right?
Yes.
So you have chosen a new basis. These are new bases.
Yes,
computational
yes,
basis,
yes.
And each computational basis is a relation.
Yes. Each computational basis is a relation. So yes, this gates basically says if x is equal to 0, then y is equal to z. Okay. That's it. Yes, and again, just to emphasize, this is naturally bidirectional, meaning that, suppose you're the one that's solving the system of constraints and you learn what y is. If this switch closes, then now you know what z is. And vice versa. If you're solving the system of constraints and you learn what z is, then now you know what y is. Okay? Okay, let me tell you how to garble this. So here's the trick. So the way the garbler, remember the garbler is not solving this system of constraints. He is setting up the program, if you like. Okay? He is going through and he's constructing an encoding. And the evaluator is going to evaluate something in some data-dependent order, but the garbler is just going to go left to right in topological order. Okay? So he arrives at this gate, and let's say that these 2 wires, he knows that the language of this wire is Lx, and he knows that the language of this wire is Ly. And what we're going to do here is we're going to say, we'll just choose our language for wire z to be Ly plus the hash of Lx. Okay, this is going to make sense in a second. All right. So this is how the garbler garbles this gate. Okay, he just says, Ly, hash the control wire, and that's how you get Lz. Okay? So in some sense, in terms of the size of the encoding of this particular computation, this switch has added nothing, because the garbler is not adding anything to the garbled circuit. At least not yet. Okay? Okay, if the evaluator comes along and she has a label on this wire, say Lx plus delta, then notice that because of the way we called our hash function, if h is a random oracle, she can't call h of Lx. She doesn't know what Lx is because she doesn't know delta. Okay? So calling h of Lx would require guessing delta for the evaluator, so she simply can't do it. Okay? So indeed, remember what this is. This is a kind of XOR secret share of the true value. If this wire is holding a 1, there's nothing the evaluator can do here. She can't compute a relation between these 2 wires in this case. Okay? On the other hand, if the evaluator comes along and there's a 0 on this wire, well, then now she has Lx, so she can call the hash function and compute the difference between these two languages on these two wires, and therefore she can freely convert between the two. Okay? Are there any questions? I'm seeing some puzzle-looking faces. I'd like to help clear this up.
Evaluator doesn't know which case.
Good. Yes. We'll come to that in a second. Any other questions? Yes.
So both the garbler and the evaluator always need to have the control wire first, and one of the, like, can't you do it the other way around, having both data wires and going to the control wire?
Going the other way around.
Like assuming you have the garbling of both data wires and getting...
Oh, okay. So if you have the garbling of both data wires, you can't get the garbling of the control wire because it's behind a hash function, right? So yeah, you can't compute that direction. Yeah.
When the control wire is set to 1, does that have some default value?
So the way that's going to, remember that the whole thing is a system of constraints. So the rule is going to be, if this switch is not saying what goes on this wire, then some other gate had better say what goes on that wire.
Okay.
Okay? Make sense?
Yeah.
All right, good. Any other questions? This is good. Okay, yeah, so the question was, the important question is, wait a second, the evaluator has to know what's on the switch in order to decide what to do. She has to know if this switch has a 1 on it or a 0 on it. Because if there's a 1 on it, she's supposed to do nothing. She's supposed to say, I can't call the hash function. I don't have the right label. Okay? And if it's got a 0, she's supposed to say, oh yes, now I know these two wires are equal, and I know the value that allows me to translate between them. So the evaluator's behavior should depend on the value of this control wire. And so let's reveal it to her. Okay? So in particular, remember, there's this thing with this point and permute bit, right? You can take the least significant bits of your shares, and now the garbler can just include in the garbled circuit a single bit that says, hey, evaluator, whenever it is that you get to this control wire, you'll learn what its value is, okay? Because my share is just attached to the garbled circuit. Just XOR it with your share, and now you know what value this control wire has. Once you know that, you know what to do, okay? Okay, but there's a very obvious problem, which is that, well, now the evaluator's learning all of these control wire values. Basically, imagine some big computation with these switches all over the place. The evaluator at the end of the computation knows the setting of every switch in the circuit. She knows whether each one is open or closed. Surely that's a problem. Okay, well, yes, it's a problem, but we can solve it. Okay? So we'll come to that in a moment. All right, so the last gate in this model, or sorry, second gate in this model is a simple XOR. Okay? Take two wires, add them together to compute the third one. This is completely free. This is the observation of Vlad Kolesnikov and Thomas Schneider from almost 20 years ago now. Wow. Basically that because these things are additive secret shares of something times delta, just add them together, you get the right thing. And I'd also like to point out that this is very obviously multi-directional because if I know x delta and z delta, I can compute y delta, okay, if I'm the evaluator. So again, the garbler is going to garble this thing from left to right. The evaluator is going to, as soon as she gets two values on any two wires, she can solve for the third one just by doing XOR. Okay? Okay. Now the third gate, let me first just say what it is, and this might raise some questions. The third gate just says, suppose you have two values, two wires, x and y. It just says, yeah, those are the same wire. Okay? And the way that you encode this particular gate is, all right, the garbler is garbling, and let's say he figured out the language for this wire is Lx, the language for this wire is Ly. He just sends to the evaluator the difference between those languages. Okay, and that will allow her to freely translate between. Because she'll get some value here, perhaps, with language x. She XORs in this difference. She gets something with language y, and vice versa. Okay? Okay. So one thing I want to emphasize very strongly is that really the only thing that we did, we had some with our switch, we added sort of one bit to the garbled circuit. In fact, in a lot of cases, you can even elide that because of this point and permute trick. But really the only thing that's contributing to the size of the encoding of one of these switch systems is the number of joins. Because the only place the garbler adds something really significant to the garbled circuit is when he adds something of one of these differences between labels, which remember are length security parameter. Okay, so each one of these join gates, is costing you lambda bits. Okay, so an interesting thing here, well, first of all, I think there's a natural question is like, wait a second, do you even need these at all? Because all you're doing is saying that these are two wires, and I'd like them to be the same wire. Why didn't you just name the same wire? And the second thing is, perhaps more importantly, you can sort of reformulate your goal of trying to shrink the encoding of a program to reducing the number of joins that appear in the program. If you can reduce the number of joins, the size of the garbled circuit encoding goes down. Okay, so we'll see an example of that. Okay, but let's get to that first point, which is, wait a second, why are joins necessary at all? And basically the reason they're necessary is because, remember, the garbler is not evaluating this thing like a system of constraints. The garbler is proceeding from left to right, topologically through this thing. Okay, so he's going through this thing, and let's say that there are two switches, and the garbler garbles both of these things. And now we'd like to say, well, actually, this is supposed to be the same wire. Okay, so you might consider conceptually just saying, yeah, they're the same wire. But if you think about it carefully, this is completely incoherent. It doesn't make any sense. And the reason is that, remember, the garbler starts with languages, let's say on these 4 wires. He computes the languages for these 2 wires separately. And now you've got 2 languages on 1 wire, and that doesn't make sense. Okay? Which one is the actual language on the wire? Okay, remember, each wire is supposed to have its own language, one language. So this just doesn't make any sense. So the resolution of this is basically you just stick a join in there, and now it makes sense. Okay? Questions on that? Because I think this is perhaps one of the main points. Is there a question?
Is this wire not going somewhere? It kind of like...
Oh, yeah. So we'll see an example of this and what to do with this exact configuration, actually, in one moment.
Do you have a proof that without this gate, there is an expressibility problem? It's just a methodological issue.
You would end up with garbled circuits of size 0 if you did not have this gate. Genuinely, you could do Boolean circuits of size 0 if you didn't need this gate. Like if it were possible to do this for free.
You said 1 bit. You said 1 bit for the switches.
Yes, you can remove that 1 bit. In many cases.
For the switches?
In the case of doing a Boolean circuit, you can remove that 1 bit.
0 bits, right?
Okay. All right. So yeah, I guess I don't have a formal proof that you don't need it, but basically something intuitively goes very, very wrong if you somehow don't have. If you can work in this model and insert no joins and compute something useful, something very strange has happened. Okay.
So one question. So maybe I'm confused, but if I'm thinking about the control bits as something which is non-secret in some cases, because you call them control as opposed to data, then it seems that once you fix the control bits, everything is just linear, right? I mean,
yes.
So how can this computation can be meaningful if all that you do is just linear operations?
Oh, okay. Let's prove it. Let's prove it's complete.
No. So again, the question is very precise, without a proof. Say that all the control bits are fixed. Is your thing computes a linear operation?
Yes, at that point it computes a linear operation.
Okay, so I have to talk about the case where some of the control bits are what I think of as data items, right? It's not just control.
Yeah, that's right.
They must be secret.
I see. So that yes, you have to think about the case where the control bits have data in them. Yes.
Okay.
Yes. Mm-hmm. I see. Okay. Yeah.
We throw out our AND gates. No longer want them.
I will show you how to construct AND gates from this now. And part of my point is going to be, this is going to be one of the state-of-the-art ways to get AND gates in a garbled circuit is going to be obtained by doing things this way. Okay? So in other words, again, your first approximation for garbled circuits should be Boolean circuits. I'm saying this is a good second approximation. One piece of evidence for that is that naturally, when you build a Boolean circuit out of this, you get one of the state-of-the-art approaches for Boolean circuits. Okay? All right. Yeah, so this is just sort of summarizing the costs of these things. And so this slide, I'm hoping to point out that there is something that's saying this is kind of corresponding to the fundamental things you can do if all I give you is a hash function. because roughly the switch says something like call the hash function. That's more or less what it's saying. The XOR gate says add two wires together. The join gate says send some data. Okay? And those are, in some sense, the fundamental things that you can do inside of a, in a protocol based on garbled circuits. If all I do is give you a hash function. Okay. Again, there is this issue of for switches, you need this one extra bit of communication. You'll just have to trust me or talk to me offline that in many, many cases you can get rid of this. It's not necessarily essential. Mostly it's here for presentation purposes that you have to reveal all the control wires to the evaluator. Okay. Okay, so let's see that this model is complete. Okay, so you can compute anything with this model. My point here is not that this is the way you should do things. Of course, my point is you want to do better than Boolean circuits. But what I want to show you is that Boolean circuits can compile efficiently to switch systems, just to, first of all, get your feet wet that this can actually do interesting things. And second of all, to prove to you that, yes, this is a complete model of computation. You can compute anything. Okay? So I claim that this, so first of all, we need to do Boolean circuits. So it's sufficient to give the Boolean basis of gates. XOR gates and AND gates would be good enough, and the constant 1, I guess, but we have that. XOR gates we already have. Those are part of the model. So all I need to show you is an AND gate. Okay? I claim this thing on the slide is an AND gate. So what does it say? Well, there's two switches, right? So it says, well, if x is a 1, then this will evaluate to 0. This switch will close, and y will flow through. Okay, onto the output wire. If x is a 0, then this switch will close and 0 will flow through onto the output wire. So as computing the function y, if x is 1 or 0 otherwise known as x times y. Okay? Okay, but this gate leaks x, again, because x is appearing as a control wire. So the point is, again, that yeah, the data is appearing on the control wires, which seems to be a problem. So let's fix that. Okay? This gate is currently not a private thing. You can't build privacy-preserving computation this way. So let's fix that. So to do that, and this is going to be my most verbose slide of the talk. Basically, there is a notion, very natural notion, of an oblivious switch system, which just says, OK, the evaluator is going to see all of these switch control wires all over the place. She sees everywhere whether the switches are open or closed. You should be able to simulate that. OK, that's it. All right, so in particular, you have to take in some randomness to make this make sense. So now your switch system takes in an input and also some randomness drawn from some distribution. And at the end, you can look at the control wires and say, I have no idea what the input was. OK? All right, so let's build an oblivious AND gate. And the trick is, what we're going to do is straight out of, again, one of the state-of-the-art papers is we're going to take two of these so-called half AND gates, which leak one of their wires, and we're going to combine them into something which is oblivious. And the trick is, hopefully all of us sort of know, maybe if you don't recognize it immediately, but just use a beaver triple. Right? This is sort of the point of what beaver triples do, is they do some kind of de-randomization such that you can do some kind of multiplication where you know one of the values. Okay? So in particular, I'll take two of these half AND gates, and what I'll do is I'll compute x plus alpha, where alpha is some random bit, times y, and y plus beta times alpha, where beta is some random bit. Well, now this leakage I can simulate because alpha and beta act as one-time pads. Okay? And now I just sort of add things together and I get x times y, but this time I can simulate. Okay? And again, I claim that this is pretty much spot on exactly what happens in this paper, 2 halves make a whole, which achieves, so for AND gates, it gets 2 lambda bits size encodings of AND gates. Okay? Yes, and to get rid of this 1 bit per switch, you basically say choose alpha. For those that are very familiar, choose alpha and beta to be your color bits, and then you're fine. You don't need to add more. I won't say more about that. I think this is just confusing people. OK. Yes?
Do the lower bounds also apply to this switch?
Oh, yes, absolutely. The like linear lower bounds, yes, absolutely, they apply here. Yes, so again, one thing I want to say is, going back to the very beginning, the point of this talk, this isn't telling you how to do everything in a garbled circuit. It's supposed to give you a lens on a lot of techniques that work. So in particular, Mike Rosalek and Lance Roy are both in the room, came up with this amazing technique that gets you roughly 1.5 lambda bits per AND gate, and that does not seem to fit into this model, at least not yet. Okay, but that's not really the point of what I'm trying to say here. Like, you can make more sophisticated things, but this is a good approximation of what a second order approximation of what garbled circuits are capable of. Okay. Okay, so let's do something more interesting. What I want to leverage is, again, this fact. So we're going to work towards multiplying values inside of a garbled circuit based on this switch system abstraction that I've given you. And one of the high-level things I want to bring back up is that these joins, the things that just say these two wires are equal to each other, that's the only place where our garbled circuit grows. And everything else is in some sense free, right? Our encoding does not grow from those gates. We'd still like to reduce the number of those gates because we pay computation for them. But if we're mostly concerned with the size of the encoding, we just have to worry about the number of joins in our model, in our particular switch system. So let me just put up here a particular switch system. I think this looks scary, but it's very simple. So what I have here is going to be an example of scaling by a constant, what's called a one-hot vector. Okay? So a one-hot vector is just a vector where all of the wires are 0 except for in one position there's a 1 there. Okay? Now we may not know where that one position is a priori, okay? But as the circuit runs, we're statically assured somehow by the structure of the switch system that only one of these wires is going to get set. And my point here is going to be this problem. What we want to do is take this one-hot vector and scale it by some value s. Okay? And the reason I want to show you this is because this is something non-trivial that you can't really do efficiently with a Boolean circuit. If you wanted to do this with a Boolean circuit, you're really going to have to pay an amount of communication that scales with the size of this vector. Right? Because you're going to have to multiply this bit by s, and this bit by s, and this bit by s, and so on. Okay? But this system, I claim, does it in one shot, which is it just does this, right? So if we imagine these are all zeros and this one's a 1, well, what happens? All of these switches close, except for at this one particular location. Remains open. So what happens? All of these wires become zeros. Well, this wire, what is it? I don't know yet. So the evaluator here is looking at this switch system, and she's trying to solve it. She's able to put a 0 here, a 0 here and a 0 here, encodings, I should say, of these values. And she has an encoding of the output. Well, there's only one thing to do, right? This must be s. Okay? So in other words, we took this one-hot vector, where the one-hot position, we didn't know where it was, and we scaled it by s while using only one ciphertext. Okay? So this is something non-trivial that you can't do with a Boolean circuit. Okay? Because you're going to have to individually multiply each of these wires by s because you don't know which one is the one-hot vector a priori. Okay. Questions on this slide?
Why did we need the join in the output wire? Not the output wire, the wire connecting.
Yeah, why? So if you don't put a join here, then what this system would be saying is that there is a wire, the output of this system, whose value is whatever this wire's value is. But this wire's value is not constrained. So if there's no join here, then both of these wires are unconstrained. Because nothing is enforcing what they are. If you want to set this wire, you can just say, oh yes, I have some other wire in my circuit whose value happens to be s. I'll just connect it, and now it goes here.
What's the output of this gadget?
Oh, good. Yes, so good. The output is these wires. Thank you. I meant to mention that. Right? This is the vector scaled by s. Okay? Yeah.
It's very silly, but like s is just some number.
Think of s as a bit for now.
Oh.
And of course, if you wanted to scale this vector by more than one thing, you could do this repeatedly. Yeah. Okay. Okay, but this is the point is this is a non-trivial task, and we're going to use it to multiply numbers in a second. Okay. Let me just mention that this technique is sort of similar in structure to other things in the literature like puncturable PRFs or distributed point functions, but it's in a slightly different setting, and there's something unusual going on where the evaluator sort of knows exactly where this one hot location is, which is not common with other techniques. All right, just wanted to mention that connection. Oh, the fact that you're sort of getting so a distributed point function is conceptually placing a 1 at a particular position of a long array. You can do the same thing here. So okay, I should have mentioned that suppose you want to build a really long one hot vector. Okay, you can do it by using this gadget recursively. Okay, you sort of build up the one hot encoding in log n steps, and that procedure, I guess, is very similar to what happens with distributed point functions in the distributed setting. Okay, if it's not, I don't want to linger on it too much, but yeah. Okay. Let me mention now that already this gives you sort of new things. So for example, I don't want to show the construction because it's very detailed, but once you can multiply a one hot vector by a bit for very cheap, you can do some relatively interesting things. Like if I have two vectors, 2-bit vectors, and I would like to compute their outer product, then you can do it more efficiently by using this gadget. Right? You can sort of save some computation because, again, you're sort of multiplying a whole vector by a bit at cost 1 ciphertext, which you can't normally do. Okay, but I want to use it right now to do something more interesting, which is to multiply numbers. Okay. Okay, so let's use this gadget as the main component of how to multiply numbers inside of a garbled circuit. So here's going to be the idea. What we want to do is we have some arithmetic circuit, right? So our goal is to compute arithmetic circuits inside garbling. And we have some L-bit integers, which is, let's say, modulo some arbitrary m. And what we want is a garbled encoding whose size is just L times the security parameter. Okay? So contrast that with like using a school book multiplication algorithm where this would be L squared. Okay? And again, the idea is going to be we're going to take each of the gates from our arithmetic circuit, and we're going to compile it into a component, into some Oblivious switch gates, switch system gates. Okay? All right. Okay. I just wanted to flash up some results. There are lots of works in the space of how to do arithmetic circuit inside garbling. What I'm achieving here is basically addition costs L by lambda, multiplication costs L by lambda. It's sort of the best that's known in this mini-crypt setting. There are other techniques that also do better that require public key cryptography, and there's many techniques in the symmetric key. Yeah?
Just using information theoretic tools like branching programs mod P, or mod M, whatever you call it, how would the complexity grow? No hash functions. Or you can do it if you want.
I don't quite understand the question. So
you can do garbling without hash functions at all. As you said
oh yes, yeah. Okay, good question.
Without going through Boolean circuits.
Yeah. So I'm going to rule those out by saying that I want an arbitrary deep arithmetic circuit.
I see. But for how deep you need it in order to beat the
not
if I want tomorrow, I have a computation, I want to use the best method in the middle.
So I mean, even at like log depth, I think this will start winning, but I haven't checked that precisely yet. Okay. Because the multiplication, it grows quadratically in the depth.
But you talked about a single multiplication, so I think for a single multiplication,
Good. Yeah, so the point is that it's compositional, right?
The lambda overhead.
Good, yes. The lambda, guys, is the downside, but again, it's arbitrarily compositional, I guess is my point, yeah. Yeah. Okay, so to do this multiplication, I'm just going to make one small generalization, which is going back to these preliminaries, I talked about these labels as being XOR shares. Let's just generalize that to being additive shares. Okay, additive over some, let's say, ring Z mod 2 to the k. Okay, so what are our labels? Instead of bit strings of length lambda, they're now vectors of length lambda, where each entry is a element mod Z 2 to the k. Okay. Everything naturally generalizes here. But the important thing I want to point out is that the languages and the labels are now bigger. Okay, this is not saving the in terms of the size of the encoding of the wires. It's going to save in terms of the encoding of the circuit itself. Okay, so the labels and the languages are now k times longer. But the benefit of doing this is that now we get free addition over integers rather than free XOR. Yeah, and really the only thing we have to do to make this work is say that, for these join gates, rather than sending the XOR difference of two languages, we just send the arithmetic difference between them. That's really kind of the only difference in the garbling of this. And the cost goes up. Okay? If these are mod 2 to the k, this costs k by lambda bits. Okay, so the join gate is bigger because the languages are bigger. Okay? Yeah? You can do, in this particular case, you can do division if you're dividing by a constant and you know it's going to divide in.
I'm more curious, like AES, I can do inverse over Gaussian field.
Okay, yeah, so this is not going to do that. Yeah. Okay, so how to multiply small numbers x and y. So let's suppose we have two small, I'll say more about what small means in a second. But two small numbers, x and y, and we want to multiply them. So how should we do it? My claim is that this thing here essentially achieves the task. So let's suppose we have our wire x, but our wire x is encoded as a bit string, a one-hot bit string of length 2 to the k. That's why small, by the way. Okay? We can only afford to enumerate so many before this encoding gets too large. Okay? So this, whatever, we have this long vector of wires, and the xth position is going to be a 1 encoding x. Okay? And over here, we're going to place y. So what is this doing? It's placing y at the xth position of this vector, this particular vector. So, was there a question? No. Okay. All right. All right, so now we have this vector. And so now what we can do is we can just do some addition gates, right? We have addition gates. We can do some addition gates to say, take this wire, multiply it by 0, take this wire, multiply it by 1, just multiplying them by constants. Okay? Well, in this particular case, since this is a 1, that means that x is 2, right? Because the second wire is the one that's on. Okay? So what's happening here is I'm multiplying y by 2 and adding everything up. That means I'm getting x by y. Okay?
It's like a lookup table, right?
It is a bit like a lookup table, yeah. Mm-hmm. But it's a lookup table with the important caveat that the evaluator knows which entry of the lookup table they're looking at, right? Because the evaluator knows all of how the switches are going, so she knows that she's looking at the xth row of this table. But that's right. This is sort of achieving a lookup table. Okay. So I don't have enough time to really flesh out exactly how to get, arithmetic circuits over any modulus ZM. It gets pretty hairy, but this is really the heart of the construction. This is sort of the main thing, is that you can achieve this. And let me try to point out what's going on here. We have, everything's backwards. Okay, this join gate costs k times the security parameter many bits. Okay, so this multiplication, and there's no other garbled material, no other encoding material anywhere for the circuit except for this one join gate. Okay, so this multiplication is just costing k by security parameter many bits. Yeah.
What is the overhead
2.
2? Is it? Oh, okay.
Yes. Yes. So
Would you describe it as kind of generic in some sense?
generic in what sense?
Like the technique, just for every single switch, you replace it with 2 switches, or you have to be more sophisticated?
So let me say what you do to achieve obliviousness. You do the thing I just presented is kind of a half multiplier, where you learn x, but not y. So the trick for getting obliviousness is exactly the same. You use, as in the Boolean AND case, you introduce a beaver triple, and you use 2 of these half multipliers to get multiplication. Okay, and one thing I want to point out here is this procedure that I showed here, what it really did is it took some kind of one-hot encoding of x, and it multiplied it by y. So this is not exactly what you want, right? You want something that takes x and multiplies it by y. There is a way to do this with a much more complicated switch system that I don't have time to describe today. But basically, it's leveraging all the same principles, which is that these gates are just expressing constraints between the wires, and you just set up a much more complicated set of constraints, which sort of converts x into a one-hot encoding and then multiplies it by y. Okay. And yeah, roughly what that system does is it does some kind of bit decomposition on x, and simultaneously turns it into a one-hot encoding. Okay. And again, really, this is the heart of how to do arithmetic garbled circuits with in mini-crypt for any depth circuits, where all you have is a hash function. And basically what you do is this part that I've showed here is sufficient for integers that are small enough. Okay, again, why small enough? Because I have to write down the one-hot encoding of these numbers, which will grow exponentially. But if my numbers are short, like if they're logarithmic in the modulus I actually care about, then this is OK. I can afford this. So really the main thing I sketched here is how to take some kind of short integer arithmetic and compile that to a switch system. And then what you can do is you can take integer arithmetic over any modulus that you want and reduce that to short integer arithmetic using the Chinese remainder theorem. And then there are some tricks that are needed here to do this efficiently with using properties of switch systems. Once again, like the linearity of the addition operation. But this really what I showed is the main challenge. How do you take 2 numbers and multiply them inside the garbled circuit in this fashion? Okay. Okay, so again, I didn't have time to talk about RAM, but basically, just to step back again, I really do think that this view, I know it's complicated the first time, but these switch systems really do sort of embody a very, I think, interesting set of techniques that you can use inside a garbled circuit. It sort of tells you what, as a second approximation, you can actually do. Again, the evidence for this is that currently these switch systems give the best constructions that we know for garbled RAM and arithmetic garbled circuits. And again, also these techniques that I shared today, like this out-of-order evaluation, this ability to sort of shrink the number of joins, also helps with things like implementing lookup tables inside garbled circuits and things like this. And I think it's very nice that it's unified by a single model of computation. I think at the outset, this doesn't feel very natural, but the more you think about it, the more natural it feels if you're working in this space. That, yeah, it's like, yeah, a switch is just evaluate the hash function. And a join is just add something to the garbled circuit. Yes. So some remaining challenges I'd like to point out. So actually, I talked today about the two-party setting. Very naturally, actually, these techniques that I described, the garbling of these gates, very naturally extends to the malicious and multi-party setting. That's not very hard. But if you think about what I said about obliviousness, you need to be able to sample from a particular distribution D. Like you need beaver triples, for example. Okay? Or maybe you need some kind of beaver triples that work in this arithmetic setting. And sampling these distributions in a multi-party setting in a way that they're friendly with the garbled circuit, that's a more challenging problem. Okay? But if you solve that problem, you could port some of these results to the malicious and multi-party setting. Another question which I think is pretty interesting is, well, I showed you, 1 or 2 tricks that you can do with these switch systems, but I sort of know that there are other things you can do as well. And I guess my question is, like, to what extent can you leverage this ability to go in two directions to improve certain computations. And as a final question, can insights from this model be applied elsewhere outside of garbled circuits, where maybe there's some other place that naturally has this idea of, you have some kind of function which one of the parties either can or cannot evaluate, and if they can, then logically things connect. Yeah, yet to find anything besides garbled circuits where this makes sense, though. OK. Yes. So again, the final message here is, if you're thinking about garbled circuits, if your mental model is Boolean circuits, that's wonderful. But if you want to think one step deeper, understand how it's possible to get efficient RAM, memory inside of a garbled program, this Oblivious switch system model is a good way to think about what's going on. OK. And I will stop there and take any more questions.
So the specific construction you described is in the random oracle model, but it doesn't seem that you're using the random oracle in some substantial way. So are these systems something that can be instantiated somehow in the
So the technical property of the hash function that you need to get switch systems to go through is what's called a circular correlation robust hash function. So there is some kind of concrete property that you can state. I just didn't include it because it's very technical.
But is there a possibility of perhaps instantiating this with other?
I believe there is I can't remember who the authors are. There's a very recent work that showed that there is a variant of this that you can instantiate. You need I/O or something to do it. But it's evidence that, yeah, it can plausibly be instantiated. Yeah?
So the main purpose of this model is to allow you to evaluate in different orders, and it seems like the examples you're showing, the relations are all ones that you could just sort of easily pick an order and solve.
Yes.
But it seems like more generally, because you have this these XORs and the switches, that it might require doing Gaussian elimination to solve these. Is there any situation where it might be useful?
Okay. Is there any situation where you can do? So first of all, the evaluator can do Gaussian elimination. I don't know what it's useful for. But yeah, you can do that.
More questions? Thank David again.
Thank you.
We have a break now, and we'll reconvene at 3:30.